Yeah, so with all these different specific or more general or whatever models of biclusters, we may lose a little bit the big picture out of sight, which is absolutely fair enough. So here is the big picture. So we looked in the context of bicluster models. We looked at the patterns in the data matrix actually, and we had the more general and the more specialized models, starting from the very special model of constant biclusters, where we have no change in the values, and then we changed, or we allowed a little change in columns or in rows, which gave us the constant columns and constant row variants of the specific model of constant biclusters. Yeah, so we allowed changes in columns or changes in rows. Changes in rows or changes in columns, meaning that we have still constant columns or constant rows, but not everything need to be constant. So that was the first generalization, and the next generalization was that we may have the change of values by the same quantity in rows and columns, but the change need to be by the same quantity. So we have some kind of shifted patterns. These coherent values, these biclusters with coherent values, are actually called pattern-based clustering, pattern-based clusters. Yeah? So that was actually the generalization of allowing not only row changes or column changes, but allowing rows and columns to change, but with the same quantity actually. Yeah? And then we even get rid of this the same quantity, but just required the same shift, the same direction, which gave us these coherent evolutions. Yeah, so that is the pathway from the very specific constant biclusters, allowing different different types of changes to up to changes of values in the same direction without having needing to have the same quantity, which gives us these coherent evolutions. And if we look at the spatial patterns of these different bicluster models, we don't see a kind of order of generality as we see it here in the matrix patterns, which is not absolutely surprising, because the matrix view is a different view than the spatial view, obviously. Yeah, but here we see it once again in this big picture here. So constant biclusters as a spatial patterns are axis parallel points or clusters located on the bisecting line, and then constant rows gives us axis parallel clusters. Constant rows gave us axis parallel sparse hyperplanes, and in the projected space again we had this bisecting line, and then we had this combination here in the coherent values, where we had axis parallel sparse hyperplanes, and in the projected space, so projected on the relevant subspace, the points are located on these increasing lines, which are also specific correlations, positive correlations. Yeah, we'll have next week the thing on correlation clusters. Yeah, so here at the first time we have we account for correlations among the points. Yeah, but in that case only simple positive correlations. Yeah, here everything is again only about relevancy and irrelevancy, nothing about correlation actually. Yeah? Coherent values allow for one specific correlation, positive correlation, correlations among the corresponding columns, the participating columns of the bicluster. And the coherent values, we have these state transitions which end up in grid-based axis parallel clusters, and if we just say we want to have change in the same direction, we end up in these half spaces, yeah, which are not really classical cluster patterns. Both of them are not really classical cluster patterns, especially those half spaces. Well, grid-based approaches, of course, we somehow know from clique and stuff like that, but the grid cells need not to be very small actually. Yeah, but anyway, that's the spatial pattern. So you see here that again, all these different models end up in different spatial patterns. So depending on what you actually want, or well, if you know what you want, depending on what you want, you can try out different things. The other way around, if you don't know what the outcome should be, then this somehow should give you a kind of intuition what you can expect as results, or what the results of different clustering models could somehow give to you. Yeah? Okay, so the only question that remains so far is how to actually compute those things. So we just talked about the model, how these clusters should look like, but we didn't talk about how to actually compute those models, those clusters. And we will do that in the following here, but just very briefly. Yeah? And we start with algorithms for constant biclusters, because this is one of the classical clustering problems stated already here 50 years ago by a statistician, Hartigan. Actually, he was doing that for bioinformatics problems, and so this is basically the birth, probably the birth of these biclustering algorithms actually. Yeah? And Hartigan actually proposed a quality measure for biclusters because, as we already mentioned, we cannot expect to have perfect biclusters. Perfect means that we really have these constant. Well, if you talk about constant biclusters, we in the original model we really assume that all the values are identical. But I already told you that in practice, of course, and I already told you that you can account for some kind of jitter, some kind of noise. Yeah, and in real data you cannot expect to have perfect constant biclusters, so that the values in the sub matrix are really constant, are really identical. Yeah, so we need to be aware that these values are not constant, but have some kind of variance, some kind of jitter, and that's why Hartigan actually came up with this quality measure for biclusters, which is just the variance of the submatrix. Yeah, so you take well, this is the mean, obviously, the mean value here of the entire matrix, of the entire data bicluster, yeah, and you take the actual values in all the rows and columns, and compute the error, the mean squared error, yeah, to the mean, yeah. So all the error of all the observations to the mean squared, and sum that up. Yeah, so that is the sum of the squared error to the mean, which is basically the variance of the submatrix. And that is the quality of a bicluster. So we try to obviously minimize the variance, yeah, and Hartigan proposed to do so by recursively splitting the data matrix into two partitions, yeah, and each split chooses the maximal reduction in the overall sum of the squares, so the variances of the resulting biclusters. So that is a kind of best first heuristic, best first search, yeah, because finding the perfect splits into biclusters such that all the variances of the biclusters are minimized is, of course, again, much too hard to just do it in an exhaustive search way. So we need some kind of heuristics, and in that case the heuristic is a best first split. So we recursively split the data matrix such that the resulting partitions minimize the variance, their variances, their corresponding variances actually. Yeah? And of course the best way to do that, or the optimal way to do that, if we just do that in this way, would be to get singularity biclusters, which is of course in that case we would have a variance of 0. Yeah, so the best way to do that is to just split up everything into singularity biclusters. Yeah, then we have number of rows times number of columns, many biclusters. Each of the biclusters have just one single row and column, so the variance is very simple because the variance is 0 in that case, obviously. Yeah, so that would be the trivial solution, and we want to avoid those trivial solutions, of course, and we do that, or Hartigan did that here, by comparing the reduction that we get in these steps here with the reduction expected by chance, and if this reduction is larger, then we stop, basically. Yeah? So that is the basic idea of Hartigan. So recursively split the data matrix into partitions such that we get a maximal reduction in the overall sum of in the overall variances of all the resulting biclusters in each partition, in each split. Yeah? And we stop if the new partitions, the reduction of the variance of the new partitions, if we get the new partitions, is not smaller than the reduction expected by chance. Then we stop, yeah, in order to avoid these trivial solutions. Yeah.